I received a really good question on one of the comments in one of my videos about dichloromethane, CH2Cl2. And the question was regarding the polarity. And so what I want to do here is show you how to determine the polarity of this molecule. So first, let's draw the Lewis structure. So I count the valence electrons. The valence electrons here are 14 and 2 is 16. And 4 more, we'll call that 20 valence electrons. The least electronegative atom goes in the center. Hydrogen, the least electronegative, cannot be in the center, so carbon will go in the center. And just anywhere around, I'll draw the other atoms. Now, this is always one of the big questions in my class. Where do we place the atoms? And the answer is, well, it doesn't matter at this point. You can place them anywhere around. And all we want to do in the Lewis structure is show the atom connections and where these 20 electrons go. So for example, right here, there are 4 bonds. Each one has a pair of valence electrons. That leaves us with 12 electrons remaining. And then the rule here, of course, is to satisfy the octet rule from the outside going in. So those 12 valence electrons will go as 3 pairs on this chlorine and 3 pairs on this chlorine. And this is what we want for Lewis structures. We counted 20 valence electrons, and we want to account for all 20 of those valence electrons. And so here we have 4 pairs, bonding pairs of electrons, and we have 3 and 6 non-bonding pairs of electrons, or lone pairs. And so this is what we want to see, 0 valence electrons left over. And so this is what a Lewis structure is. In 2 dimensions, it tells us the connections of the atoms and the placement of electrons. Well, this is the interesting thing about dichloromethane. Some students will draw the molecule like this. And students always ask, which is the right way, which is the wrong way? And the answer, well, let me pick that up. The answer is that both are correct. Now, for small molecules, you cannot determine polarity solely based on the Lewis structure. Remember, the Lewis structure is in 2 dimensions. It's just flat on the paper. All we want to know from Lewis structures is where the atoms are located, how they're connected, and where the electrons are, the valence electrons. In order to determine polarity, we need to know the 3D structure. So I have other videos on molecular geometry. So in short, in the 3D structure, we have a carbon atom that has 4 bonding pairs. And so this is going to be a tetrahedral geometry. It's a tetrahedral electron pair geometry, and because each electron pair is participating in a bond, the molecular geometry will also be tetrahedral. Again, I'll refer you to those videos on molecular geometry. So let me draw the wedge-and-dash structure, and let's get a better picture of what this is. And so I'll go ahead and draw it this way. The wedges, of course, mean that these are atoms coming towards you out of your screen, and the dashes are atoms going into your screen. And so you can almost imagine, here's my tetrahedral. It almost looks like a little tripod, and then there's that atom going up. So now we actually have shape to this. Okay, is the molecule polar or nonpolar? The best way to do this is to look at symmetry. Okay, and so we'll look at symmetry. It looks asymmetric. Let's look at the dipoles. Chlorine is more electronegative than carbon. So we can draw a dipole kind of coming out at you. This chlorine is more electronegative than carbon, so we can draw a dipole going into the paper. This is a little tricky. Carbon and hydrogen have very small differences in electronegativity. In some classes, your instructor might tell you to ignore that difference in electronegativity, but even if you do account for it, Carbon is slightly more electronegative, so there's almost a small dipole going towards the carbon. And what do you notice here? The electron density is being pulled from the hydrogen side, which is flat on the paper, towards the chlorine. And so you can almost draw a dipole kind of going like this. So this is asymmetric. There's a big arrow there. So this is asymmetric and polar. Now, for a better picture of this, I have built the molecule using our models. So the model looks something like this. So let me get a different page on here so we can see it a little bit better. And so here's our models that we use in our class. The carbon is the black atom. And right here, you see the two hydrogens that are in the plane. There's an atom right here coming out towards you, and then there's an atom here, the chlorine going away from you. And so notice the big difference between the 2-dimension and the 3-dimension, right? So if I hold it like this, you can see that these dipoles are kind of going from left to right, right? The electron density is being pulled this way. If I hold the molecule like this, the very small dipoles between carbon and hydrogen are being pulled towards the carbon. And so you can almost imagine the electron density is going from left to right, making the molecule polar. Now, let me show you the problem with dichloromethane. So let's go back to our Lewis structures. By the way, good example here of the wedge and dash, right? The chlorines going towards you and away from you. You can see that right here. So here's the problem with the 2-dimension, right? So if you drew the molecule like this, then you would say, well, these dipoles are going away from each other, these dipoles are going towards each other, and so they cancel. But of course, that's not right. In 3 dimensions, they don't cancel. And so you get this net dipole moment for the molecule. And so that's the problem when you try to determine polarity with the 2-dimensional structure. And just to close out this discussion, I want to show you what happens if we start changing some molecules. What happens to that tetrahedral? So for example, here's methane. Methane has all hydrogen atoms. And so, yes, there are some small dipoles here, but you notice that all the dipoles are going towards the center equally. And so this molecule is very symmetric. And in fact, you do have that plane of symmetry here. So the molecule is very symmetric, and therefore symmetric means non-polar. I want to show you the carbon tetrachloride, a very common molecule we see in organic chemistry. Same thing. You have dipoles going out towards the more electronegative chlorine, but the molecule is symmetric. All those dipoles are going away from the center equally, making the molecule non-polar.